So we're going to finish off chapter 6 today. Remember, tomorrow you guys have your quiz on chapter 6, and then your trig exam is Thursday. So that means on Wednesday we will be going through your chapter 5 and chapter 6 quizzes, and then whatever time is left, you will have to work on your review assignment that you guys got last week. So it's important that you have that done before the test. That'll tell you really if you're ready or not for this exam. If you can do everything on that review without looking at your notes, then you're ready. Okay, so it's important that you have that done before the test. It is due for March as well, so make sure you get it done. So we're going to continue looking at solving trig equations using identities. Remember, to solve some equations, you need to make substitutions using the trig identities that we've already studied in this chapter. This often involves ensuring that the equation is expressed in terms of one trig function. So we'll also be using the formula sheet here, which again you'll be given for your test. So you don't have to memorize any of these identities, you just have to know how and when to use them. So looking at the first one, it says solve each algebraically and notice the domain. It says that x is greater than or equal to 0, less than 2 pi. So if your answer is on that positive x-axis, you would state it as 0, not 2 pi, because it says x is less than 2 pi. This also tells us that our answers need to be in radians, not degrees. Okay, so for question A, you've got cos 2x. We have three different substitutions that we can use for cos 2x. But if we look at this, we also have a term that is cosine x, which tells us that we want to use the double angle identity for cosine that only involves cosine, which would be this one right here. The first one involves both cosine and sine, so we don't want to use that because in our equation we have a cosine term. The last one only uses sine, not cosine at all, so we don't want to use that one either. We want to use the one that only involves cosine, and that is that cos 2 theta equals 2 cos squared theta minus 1. In this case, it would be 2 cos squared x minus 1. And then you got the plus 1, then you have the minus cosine x. So we make the substitution, and that's what we have. Okay? So, you've got 2 cos squared x. Try that again. One more time, we'll try that again. The minus 1 plus 1 cancels. So we have 2 cos squared x minus cosine x equals 0, which we can solve by taking out a common factor of cosine x. This gives us 2 cos x minus 1 equals 0. So our solutions will come when each factor equals 0. For that first factor, it's just where the cosine of x equals 0. For the other factor, where 2 cos x minus 1 equals 0, which if you get cosine of x by itself, then it's where the cosine of x equals 1/2. So let's open up a unit circle here as well. Our solutions here in this case will be where the cosine of x equals 0. And remember, 0 is the first number at each point on the unit, cosine is the first number at each point on the unit circle. And the x value, which is the first number, will equal 0 at pi on 2 and at 3 pi on 2. But we also want to know where the cosine of x equals a half. And the cosine of x, the x value equals a half here at pi on 3, and down here at 5 pi on 3. Okay? You only need the first quadrant. We talked about that. The cosine is a half at pi on 3. Using the cast rule, you'd have to be in the C quadrant, which is the fourth quadrant, because cosine is always also positive there. And that angle would have a reference angle of pi on 3. So from 2 pi, you'd back up pi on 3. 2 pi would be 6 pi on 3. Backing up 1 pi on 3 gives us the 5 pi on 3 as well. So x will equal pi on 3 and 5 pi on 3. And you can always use your calculator to check your answers. So in this case here, we have to be in radian mode because we're going to be using angles in radians. So the cosine of 2 times, our first answer was pi on 2. So in brackets, I'm going to put pi over 2. Close the bracket on the pi on 2. Close the bracket of the cosine of 2 times pi on 2. Plus 1 minus the cosine of pi on 2. I'm checking that original equation. That should equal 0, and it does. Right, so that one works. Next, we'll try 3 pi on 2. So we'll insert a 3 there and there. That also works. We get 0. Next, we'll try, I'm going to do the 5 pi on 3 first. Okay, doing the 5 pi on 3 first. That works. We get 0. And then we'll do the pi on 3 by deleting the 5. Works as well. So you can always check the answers that you get. The only thing is that you may miss some answers, but you should never get the answers that you stated as wrong, because you can always check them on your calculator. Okay, so we checked all 4 of our answers there. You could also do it graphically, and this also could be used because you'll be able to check and make sure you didn't miss any, right? So if we look at what the graph would look like, we put that equation in there, the cosine of 2x plus 1 minus cosine of x, right? We'll set our windows between 0 and 2 pi, and maybe what we'll do is we'll just go to a little bit left of 0, say negative pi on 2 as our x minimum, and we'll go a little bit greater than 2 pi, maybe 2.5 pi. And we'll set our scale at pi over 2. We're not sure what this graph would look like. We know that if it's just cosine of x, that only goes up to 1 and down to negative 1, but in this case, there's more terms there. So I'll leave my y min and max as they are. When you graph it, here comes the graph. And we want to look and see that there is 1, 2, 3, 4 x-intercepts there. We got 4 answers. So that means we didn't miss any. But we can check them on our graph by going into the trace mode, and we manually input pi on 2 in. That confirms that's a x-intercept because y equals 0 there. Okay, if we check 3 pi on 2, confirms that that's an x-intercept, a solution because y equals 0 there. If we check pi on 3, confirms, and 5 pi on 3 confirms because y equals 0. So using the graph, you can check all your answers and also make sure that you didn't miss any. Okay, but you have to know how to solve them algebraically. The calculator is only used as a check. Question B, the equation is 1 minus cos squared x equals 3 sine x minus 2. So right now we have two different trig functions in this equation. We've got cosine and we have sine. There's nothing you can do with the 3 sine x. Nothing you can do with that. Can't change it. But can you change 1 minus cos squared x? Dylan, you're shaking your head. You're nodding. Why? 1 minus sine squared x is cos squared x. Okay, I don't disagree. So what would you write next? Right. That's what we would use. That 1 minus cos squared x is sine squared x. Now we have only one trig function here. The only trig function we have is sine x. So we would solve this by moving everything to the left, make it equal to 0. So that means you're going to subtract the 3 sine x from both sides, add the 2 to both sides. So there's our quadratic equation. Now we're going to solve, and we'll solve it by factoring. The factors will be sine x minus 1 and sine x minus 2. Negative 1 times negative 2 will give you the plus 2, and when you add negative 1 and negative 2 together, you get negative 3, which is that middle term coefficient. So our solutions will come when each factor equals 0. There we are. Our answers for sine x equaling 1. That's on the unit circle. Sine is the y value, and it equals positive 1 up here at pi on 2, and down here, sorry, that's the only place, because down here it's negative 1 actually. So only one answer there, which is pi on 2. Sine of x doesn't equal 2 on the unit circle though. But remember, just because a value isn't on the unit circle doesn't mean we can't get answers. If we though tried to find the second function sine of 2, we get an error. And remember, that is because the graph of sine x only goes up to 1 and down to negative 1. It never goes up to 2. So there's no solution for that one. Our only answer should be pi on 2. And we can check that in our graphing calculator by going to y equals and putting our original equation in there. Now, we've got to go 1 minus cos x all squared. Open a bracket because we have to square the cosine of x. And in this case, this equation, the original equation, had a left side and a right side. So we'll put the left side into y1, the right side 3 sine x into y2. And now we're going to look for the point of intersection. And there's only one point of intersection between 0 and 2 pi. Right? If I change my x max to 2 pi instead of 2.5 pi that I had before, we'll see there's only one point of intersection. Second function trace, number 5 for intersect, enter, enter, enter. Gives us that value of 1.57, which is pi on 2. See, if I go into the trace mode, and I let x equal pi on 2, it's that same point where y equals 1. Okay? So that just confirms there's only one answer, and that answer is pi on 2. All right, for this one, part A, there's only one option for sine 2x when you look on the formula sheet, and that is 2 sine x cos x. The only option for sine 2x. 2 sine x cos x. The second term is minus cos x equals 0. And this one can be factored by taking out a common factor of cos x. So our solutions will come when each factor equals 0. And that'll be where the sine of x equals 1/2 for that second one. Add 1, divide by 2. So where does the cosine of x equals 0? We've already seen that today. It's at pi on 2 and at 3 pi on 2. If we check our windows or our domain, once again between 0 and 2 pi, so we have to be in radians. We're also going to have answers where the sine of x equals 1/2. Sine, remember, is the y value, equals 1/2 there at pi on 6, and over here at 5 pi on 6. If we just use the first quadrant, our reference angle is pi on 6. The CAST rule tells us that the second quadrant is our S quadrant, where sine is positive. So an angle here with a reference angle of pi on 6 is 1 pi on 6 short of pi, or 1 pi on 6 short of 6 pi on 6. Also gives us 5 pi on 6. So there's our answers. If we check them graphically, sine 2x, whoops, let me clear that, sine 2x minus cosine of x should equal 0, which means we're going to be looking for the x-intercepts of this graph. Looks like there's 1, 2, 3, 4 x-intercepts. We got 4 solutions. To have a better look, if you change your windows, let's say between -2 and +2 on the y-axis, it'll give us a better look at those 4 x-intercepts. And to confirm, go into the trace mode, checking pi on 2. Yes, y does equal 0 there. Checking 3 pi on 2. Yep. Pi on 6. Yep. And 5 pi on 6. Yep. Okay, so not only are we confirming that there are 4 solutions, but we just confirmed that the 4 solutions we got are correct. So the calculator can be used to confirm, but you got to know how to solve these algebraically. Looking at question B, we've got a term with a cosine x and a term with a sine squared x. So we can't have that. We've got to have it in terms of one trig function only. There's nothing we can do with the cosine of x. But Edmund, what can we do with the sine squared x? I'll play your silly game, do we?
Yeah.
How? What would we do? Diego, can you bail him out? You could turn sine squared x into 1 minus cos squared x. Yeah, you could do that. Is there an easier way, though? Right. Use the 1 minus sine squared x. That equals cos squared x. Your way will work, Diego. But this is a little bit easier. So you've got 2 cos x as your first term. We've said that 1 minus sine squared x is cos squared x. That is true. Equals 3. So now we will make it equal to 0, right? We've got a quadratic expression in terms of only one trig function. We'll make it equal to 0. We also normally put the squared term first. And there's the quadratic that we will now factor. Two numbers that multiply to get negative 3, add to get positive 2 would be positive 3 and negative 1. And then the solutions come when each factor equals 0. This will be where the cosine of x equals negative 3 and positive 1. And remember, cosine only goes up to 1, down to negative 1. It'll never get to negative 3. So there's no solutions for this one. Our answers will come where the cosine, which is the x value, equals positive 1. The only place is right there at 0 radians. Remember, we can't use 2 pi radians, even though that's coterminal with 0. We can't use it because our domain says that x must be less than 2 pi, not equal to. So the only answer here that we can use is 0 radians. So if we put this in our calculator, there should only be one answer. And in this case, just because the equation has two sides, we're going to use y1 and y2. y1 is where we'll put the left side, 2 times the cosine of x plus 1 minus sine of x all squared. Right, that's our sine squared x, and that should equal positive 3. That's the right side of the equation. And because we're letting y equal 3, our y maximum has to go up to at least 3. Let's make it go up to 4. So it'll graph the curve, it'll graph the line. It shows there that we have a point of intersection at 0, 0. If you go into the trace mode and let x equal 0, that's where y equals 3. It also equals 3 over here at 2 pi, but we can't state that as a solution because our domain says that x must be less than 2 pi, not equal to. Okay, so again, calculator can be used to confirm not only that you have the right number of solutions, but that you have the right solution. In this case here, we're going to solve this one now, but we're going to be in degrees instead of radians. So that means changing the mode in the calculator. So we do have a cos squared x there. But on the right side, we have cotan x, sine x. So let's see if we can simplify this. Cotan is cos over sine, and that's multiplied by sine x, or sine x over 1. And if you write it like that, you can cancel the sine x's. So our solutions will come where cos squared x equals cos x, or where cos squared x minus cos x equals 0. So that can be factored by taking out a common factor of cosine x. Right? So you make both factors equal to 0, and our solutions will be where the cosine of x equals 0 and positive 1. In degrees now. Cosine of x equals 0 here at 90 and down there at 270. So there's our first two answers. It also equals positive 1 here, which is at 0 degrees. We can't use 360 because the domain states that. X has to be less than 360, not equal to. So those are only three answers that we should get. And part B does say verify graphically. So we will do that using the original equation. The left side will be y1, the cosine of x all squared. The right side will be y2. We don't have a cotan button, but we can go in brackets 1 divided by tan of x times the sine of x. This is where we're also going to see any non-permissive values that we have, right? When we graph it, oh, I need to change my windows and my mode. I'm going to go from, let's say, negative 45 degrees up to 360 degrees and a scale of 90. I also need to change my mode into degrees. So there we go. Second function, well, actually, let's just use the trace mode. If you let x equal 0, you get y equals 1. But notice that right now we're on y1. That's the graph of the cosine of x all squared. There's no restrictions for that. But there are restrictions for y2 because it involves cotan, which is cos over sine. The restrictions will be where the sine of x equals 0. So if I make sure I'm on that graph, and now I let x equal 0, notice I have no y value returned. 0 is a non-permissive value, so it can't be a solution. Oh, so we can cross off that one. But we also need to check 90 and 270. So checking x equals 90 doesn't work. That's non-permissive. Checking x equal 270 doesn't work either. In this case, there are no solutions to this graph or to that equation. None of them work because all three answers that we got are actually non-permissive. And the reason for that is because cotan can be written as 1 over tan. And when you write it as 1 over tan and then realize that tan is sine over cos, but because tangent is a denominator, neither sine nor cos can equal 0, which is what all three of these angles have. Either sine or cos equals 0. Okay, so in this case, there is no solutions to that one. Looking at this one. So I've got 1/2 times tangent, which is sine x over cos x, times cosine x, or cos x over 1. And when you write it like that, the cos x's cancel. So that would leave us on the right side with just 1/2 sine x. If we bring it over to the left by subtracting 1/2 sine x from both sides, there's the equation that we're going to solve by factoring. There's a common factor of sine x that we can take out. So our solutions will come where the sine of x equals 0 and where the sine of x equals 1/2. Again, our solutions have to come from degrees. So back to our unit circle. The sine of x, the y value equals 0. Whoops, try that again. At 0 degrees and at 180. We can't use 360 because the domain says that x must be less than 360, not equal to. So 0 and 180 are our first two answers. It equals positive a half. The sine equals positive a half. Here at 30 degrees and over here at 150. There shouldn't be any non-permissive value. Oh yeah, there will be, because tangent is sine over cos. We can't have a denominator of 0, so cosine can't equal 0. So we'll use our graphing calculator to confirm that. Our original equation we'll put in. In this case, we'll have to have two equations. The left side will be where we put y1, which is the sine of x all squared. The right side will be 1/2 or 0.5 tan x times cosine x. I'm in degrees. So it looks like there are looks like 3 answers. We actually got 4 answers, so that's okay, we'll check them. If we change our windows for our y min and max, going from, let's say, negative 1.5 up to positive 1.5, might give us a better look. Looks like there might be 2 points of intersection here, which will give us 4 altogether. But second function trace, number 5 for intersect. Enter, enter, enter. So there's our 150 as one answer. If we check 180, that's an answer. If we check 0, that's an answer, point of intersection. And now we just got to check 30. That's also a point of intersection. So those 4 points do work, but we just have to make sure that none of them are non-permissive. So if we go into our trace mode, and right now we're on the first equation, sine of x all squared, which there are no restrictions, but the second equation has tan x. That's where we're going to have our restrictions. So if we check our points, 0 is a point on that graph. So trace, checking 30. That is a point on that graph because we get a y value return. Checking 150. That is a value on that graph because we get a y value return. Checking 180 also is a point on that graph because we get a y value return. So all 4 points work. All 4 points work. So looking at this next one. This one says give the general solutions in radians. So we have to first find our solutions between 0 and 2 pi. So we have sine 2x equals root 2 cos x. There's only one option for sine 2x, that's 2 sine x cos x. And then I would subtract the root 2 cos x from both sides to make it equal to 0. And we would solve this one by taking out a common factor of cosine x. Which will leave you with 2 sine x as your first term inside the bracket minus root 2. And again, your solutions will come when each factor equals 0. This will be where the sine of x equals root 2 over 2. And that's on the unit circle. But our first answers come where the cosine of x equals 0. Cosine the x value equals 0 here. Up here at pi on 2 and down here at 3 pi on 2. And because those two angles are equidistant apart no matter which direction we go, we can just say that it's every multiple of pi on 2. Because we want general solutions here in radians. Now, where does the sine of x equal root 2 over 2? So that's here at pi on 4 and here at 3 pi on 4. And because those two angles are not equidistant apart depending which direction you go, if you go in a positive direction, it's much shorter than a negative direction. You have to do two separate statements, both of them with multiples of 2 pi. So pi on 4 plus 2 pi n and 3 pi on 4 plus 2 pi n, where n is an element of integers. So there's those general solutions that we've done in the past. Yeah. I'm sorry, that's wrong, isn't it? Yes. It should be pi on 2 plus n pi. Yes, thank you for pointing that out. This should have been pi on 2 plus n pi. Because you're going from pi on 2 down to 3 pi on 2. They're separated by pi radians. Thank you, Julia. Okay. So for cos 2x, you have three options. Because you also have a term with cosine on the right, you need to choose the option for cos 2x that only involves cosine, which is 2 cos squared x minus 1. Bring the cosine over. Rearrange the terms, make it equal to 0. So try this one. See if you can finish it off. We want the general solutions in radians. So the factor would have to look like that. And then you're looking for where cosine of x equals -1/2 and +1. Cosine equals -1/2 over here at 2 pi on 3, and down here at 4 pi on 3. That's where the cosine, the x value, is -1/2. 2 pi on 3 and 4 pi on 3. And those are not the same distance apart, depending which way you go. So you have to write a statement with both of them. So 2 pi on 3 plus 2 pi n, 4 pi on 3 plus 2 pi n. And then the second set will come where the cosine of x equals +1. There's only one place where that happens, which is right there. And that's every multiple of 2 pi. So 2 pi n. Where again, n is an element of integers. So looking at this one, we've got a reciprocal ratio in there. Remember, cosecant is 1 over sine. So 3 times cosecant, if I just do this on the right side here, 3 times cosecant of x is the same as 3 over 1 times 1 over sine of x. If you multiply fractions, it's top times top, bottom times bottom. So that becomes 3 over sine x. That's what that 3 cosecant x can be written as, 3 over sine x. I'm going to get rid of that denominator of sine x by multiplying every term by sine x. And the reason we do that is because that last term, the sine x's, are going to cancel. The common denominator for this expression was sine x. If you multiply everything by the common denominator, you haven't changed the value of it because you're multiplying every term by the same number or same value. But what you are doing is you're getting rid of that denominator in that last term. So when you multiply all the terms by sine x, that first term will become 2 sine squared x equals 7 sine x minus 3. We'll make it equal to 0 by bringing everything over to the left side. And there's the quadratic that we need to factor. In order to make this work, we need a -1 there and a -3 there. The outer products will be -6 sine x, the inner minus 1 sine x. That gives you your -7 sine x in the middle. Again, our solutions come when each factor equals 0. So that's where the sine of x equals 1/2 and +3. And there is no solution for that last one, right? Because you cannot have a sine of x equaling 3. It only goes up to 1 and down to -1. So our solutions only come where the sine of x equals 1/2. Again, we want to state them, general solutions, in radians. assign the y value equals positive a half here at pi on 6 and over here at 5 pi on 6. And because those are not the same distance apart on the circle, we have to use two statements by adding 2 pi n to both of those. Where n is an element of integers. So this last one we'll be doing the same way. Because 5 secant x, because secant is 1 over cos, we can write that as 5 over cosine x. And then we will multiply each term by cosine x. So that the cosine x's will cancel for that last term. And what we have left is 3 cos squared x plus 2 cos x minus 5 equals 0. And so that's what we need to factor. Would only work if we have a 5 with a 3 and a 1 there. The 5 would have to be positive. You'll get 5 cos x minus 3 cos x. Gives you your plus 2 cos x in the middle. So for that first factor, if you make that equal to 0, that'll be where the cosine of x equals negative 5/3, which is less than negative 1. So there'll be no solution for that one. But we'll have solutions where the cosine of x equals positive 1. And that's just at 2 pi or 0. So the general solutions will be x equals 2 pi n, where n is an element of integers. And like before, you can check these on your calculator, right? We've done that, lots of that. Okay, so page 320, questions 1 and 2 is what you need to do for homework. I believe I asked you that assignment from Friday, I asked you to hand that in, right? That worksheet. So if you're not done that, you might want to be working on that to get it done. Remember that you have a quiz tomorrow on chapter 6. Wednesday we'll go through chapter 5 and 6 quizzes, and you'll also have time to work on your review assignment, which is due for Thursday when you write your trig exam. Okay? Yeah.